Hello. In today's video, we're going to give a demonstration of Future's capabilities for modeling fuel and flare, or to give more details, to simple modeling of flare, and then rather more elaborate modeling, not only of fuel, but also of the power requirements that drive fuel consumption. So we're going to demonstrate it with one of Seraphim's standard demonstration models. So this is a model, an artificial model with approximately 200 producers and a reasonably complex production system. So let's focus in, first of all, at the top of the system. And here we have gas gathering, oil, water, and sales, and then we have power generation and flare. So starting with the flare, in here we're modeling it very simply. We're defining a split at the gas gathering system, and we're saying that a fixed fraction of the gas is being flared. Here it's 0.01, i.e. 1%. So this is reflecting the occasional shutdowns and the need to vent the system and so on. Now this fraction can be modified in time with planned changes. And what that does gives you here, I'll show you the forecast for the gas, something of the order of getting up to 105 million scuffs of gas, and correspondingly the flare gets up to about 1 million scuffs. So that's simple modeling of a fixed proportion of gas being flared. Fuel modeling, we're going to show you a rather more elaborate and more detailed modeling, where we first of all define the power requirements for key bits of equipment. We define the power supply from fuel and the corresponding fuel consumption from that. Okay, starting with power requirements. So here we've got something representing part of the system representing the pumps to pump the water and oil to the gathering stations and so on, to the export. And we've got under power, we've got a power requirement. There's a fixed base load, and then there is a variable element, so many kilowatts per stock tank barrel per day. Similarly, on the gas side, the compressor has a power requirement defined, and that's defined here. And Future will calculate the power supply and the power used from that, and it's included in the standard output, in the standard plots, and also in export to Excel. So the Future models the supply of power much in the same way as it models the provision of lift gas. So while production goes upwards to parents and step parents, power supply goes downwards to child and stepchild nodes, unless it's specified as, unless these certain paths are shut off with zero power supply constraints. Now, you can, if you leave the head node as without any constraints, there will be power supplied from external power supplied from the head node. But here we're going to put a constraint of 0, preventing that external power. And instead, we're going to model power generation at this node here. And that's specified under power again. And we're specifying how much fuel gas is consumed, how much gas is consumed per kilowatt of power generated. In the first forecast I'm going to show you, we're going to have constraints on the power generation. Initially 25 megawatts and then 35. And then we'll also run a second forecast without those constraints to see the difference. So here's the power generated, and you'll see that it starts off at 25 and then it goes up to 35 during this period. And the source of gas for that is from the compressor, and we've got a split here, and it's saying that in terms of the split, the solver can determine how much power's going there. There's also another point to note. I'm not going to go into much detail on this, but there's an external link supplying there's a link between this production network and a water injection network, and we've got supply of power to the head node of the water injection network. So that was a forecast. So the resultant forecast is taking into account the power generation, and you can see that when the constraint on power generation is raised, then you get a corresponding jump in oil production. To illustrate this further, let's run a forecast with no power constraints. And I've already defined it, and here we're omitting the power constraints defined in those plan changes. So running the two forecasts for 50 years, monthly time steps, 200 wells. It's most of them are under rate constraints. A few of them are under pressure constraints. We get the answers in a few seconds. And see at the sales node the difference forecasts. So this is without the power constraints, and then the darker one is with the power constraints. It should be noted that with this modeling of power and fuel gas, you can specify constraints at basically any part of the system. You can specify constraints on power supplied and so on. And the solver handles it all together with the choice of flows. So you get a forecast that maximizes the value of production while honoring all the fluid handling constraints, not only all the fluid handling constraints, but all the power constraints, and hence a detailed calculation of fuel requirements. Thank you for your attention.